Welcome back to Math 111. This is part 3 of Chapter 7 on Basic Probability. In part 1, we introduced the basic concepts of probability and random variables. We focused on discrete random variables in particular. And then in part 2, we discussed expectation, standard deviation, and binomial random variables. Now in part 3, we will move on to continuous random variables and then using them to approximate binomial random variables. Make sure you have the necessary packages loaded, require Mosaic and require Tiger Stats. And let's get started. Before defining a continuous random variable, let's think back about the definition of a discrete random variable. A discrete random variable was a random variable whose range consisted of whole number values. A continuous random variable, on the other hand, is a random variable whose possible values lie in a range of real numbers. So for example, the amount of sugar in an orange could take on any positive value. Likewise for the heights of students at Georgetown College. If we were dealing with a random variable that was defined to be the student percentage grades in Math 111, the range would be the closed interval from 0 to 100, 0% to 100%. Very simply put, a continuous random variable can take on whole number values as well as decimal or fractional parts. When we viewed the PDF, remember the probability distribution function, for a discrete random variable, we looked at tables and then we looked at histograms. Since a continuous random variable can take on numbers in a continuum of values, the PDF of a continuous random variable cannot be viewed as a table or a histogram, but rather it's viewed as a smooth curve. There are lots of types of continuous random variables, but we will only be discussing one type in this course, the normal random variable. There's some really nice features of a normal random variable. Its PDF is known as the normal curve, and it looks bell-shaped like you see here on the right. Continuous random variables have an expected value and a standard deviation, just like discrete random variables do, and the interpretation of those values is the same. A nice feature of the normal curve is that it's centered at and symmetric about the expected value. Oftentimes we refer to the expected value of a normal random variable by the Greek letter mu. You see that right here. So the expected value tells you where the probability distribution function, or the normal curve, is centered. For this example shown here on the right, you can see that it's centered at 0. So the expected value for this normal random variable must be 0. The standard deviation of a normal random variable tells us something about how spread out the normal curve is. In other words, standard deviation controls if the curve is really narrow and skinny or if it's more spread out and wide. Another Greek letter is used here to describe standard deviation. That Greek letter is sigma, and you see it right here. One final feature of the normal curve is that the 68-95 rule applies. So let's talk about that. There are 3 parts to the 68-95 rule. The probability that the value of a random variable falls within one standard deviation of the mean is approximately 0.68 or 68%. So we've written this statement in math notation right here. Remember, mu is the mean, or the center of the curve. Mu minus sigma would be one standard deviation below the mean, and mu plus sigma would be one standard deviation above the mean. So the inequality that you see here in the probability says the value of the random variable x is bigger than one standard deviation under the mean, but it's smaller than one standard deviation above the mean. In other words, the value of x is within one standard deviation of the mean. And this probability is about 0.68. The next 2 statements are similar. We're just now going out 2 and 3 standard deviations. So the probability that the value of the random variable x falls within 2 standard deviations of the mean is about 95%, 0.95. The probability that the random variable x falls within 3 standard deviations of the mean is about 99.7%, or 0.997. Putting this another way, there's about a 99.7% chance that the value of the random variable will be within 3 sigmas of mu. Let's do an example. Suppose you know that the heights of college males follow a normal distribution with mean 72 and standard deviation 3.1 inches. If the random variable x is defined to be the height of a college male, then about 95% of college males are between what two heights? In other words, we are looking to fill in the blanks in the probability statement here. When you see a problem involving 0.68, 0.95, or 0.997, you should immediately think of the 6895 rule. The Empirical Rule GC app in R provides a nice visualization of this. So we'll input the mean of this distribution and the standard deviation and run this in R. So let's just select this code, and I will copy it, and then I'm going to click over to our studio and come down here into my console and paste it. And in your plot window, you should have something like this pull up. So you're dealing with the 6895 rule here. Now, it's listed as the empirical rule. That's just another name for it. We're calling it the 6895 rule in this class, but you'll probably hear it referred to as the empirical rule as well. So we have set the mean to 72, we've set the standard deviation to 3.1, and we have this nice normal curve here. Notice it's centered at 72. Up here in the manipulator wheel, if you click on it, you'll see a few things that you can play around with. So the first thing that you can do is you can change the range that you're looking at. So right now it's set to mean plus or minus 1 standard deviation. So it's talking about the first part of the empirical rule. You could change it to mean plus or minus 2 standard deviation. So this would be the second part of the empirical rule. And notice that the shaded region here changed from roughly 68% to now roughly 95%. Now if we change it and go up and down one more standard deviation, you'll see that now we've captured about 99.7%. So what we're looking for is we're looking to fill in the blanks in the statement. The probability that x is between what two values is roughly 95%. So we know we're talking about the second part of the 6895 rule. So let's go back to that. So here on the graph, we can see that this inside region is about 95%, and we see that the bounds on the inside region are 65.8 and 78.2. So our answer would be about 95% of college males are between 65.8 inches and 78.2 inches tall. The way that R arrived at these numbers was by simply adding and subtracting two sigmas, or two 3.1s from the mean. So 72 minus 3.1 minus 3.1 got us to 65.8. And then 72 plus a standard deviation plus another standard deviation got us to 78.2. You can flip through the pickers to see that you can find various probabilities or values using this app. So suppose instead you were interested in knowing what percentage of college males are taller than 78.2. So if you think about that, you know you're looking for 78.2 or bigger. So we're talking about this region right here, this little tail that's not shaded in. So if I want to switch the shading on the graph, I can just go to this picker and switch from between to outside. And now the outside is shaded along with the appropriate percentages. So we could say that about 2.5%, about 2.5% of college males are taller than 78.2 inches. So let's click back over to the slides. You should play around with this app a little bit and just kind of get used to inputting different means, inputting different standard deviations, and playing around with the pickers. Okay, so while the 6895 rule is really useful, you need to keep in mind that it still is just an approximation, although it's a really good one in many cases. So if we wanted to compute probabilities that can't be determined using the 6895 rule, we can use a function similar to something we saw in part 2. So for a normal random variable, we will use the function pnorm_gc. It works much the same way as pbinom_gc did in part 2. The arguments now, instead of being the size and the probability, when talking about a binomial random variable, now the arguments are the mean and the standard deviation, since we're dealing with a normal random variable. So suppose we want to compute the probability that the height of a college male, the value of this random variable x, is bigger than 70.9. So the height of a college male is greater than 70.9 inches. Well, we could just run this line of code. Here we're outputting a graph. The graph this time, instead of being a histogram that goes with a binomial random variable, it's going to be a normal curve because we're talking about a normal random variable. And we get 63.86% or 0.6386. Since this was a greater than inequality, it was a right tail probability, which is what you see here in the graph. We can do all of the regions that we did with p binom GC. You could do region equals above, region equals below, region equals between, region equals outside, which we haven't seen. We'll get to in just a second. However, with this function, there is no need to think about doing any kind of a shift. This is because we're dealing with a continuous random variable now. So if we're looking for something like x strictly greater than 5, there is no equivalent for this using greater than or equal to when you're dealing with a continuous random variable. So like I said, one region that we didn't look at in part 2 with p binom GC was region equal outside. Suppose we wanted to know the probability that the random variable x took on a value less than 69.4 or it took on a value greater than 79.1. We would enter these two bounds in as a list using the concatenate function here, as we did before. And then we're going to set region equal to outside, keeping the appropriate mean and standard deviation, and we get about 21%. You can see here in the graph that we have two regions shaded, one for the probability of being below 69.4 and the other for the probability of being above 79.1. We add these two areas together and that's where we're getting 0.2118. So in all of the previous examples, you were given the bound and you were asked to find the probability. What if we switch this? Suppose we give you the probability and we want you to find the bound. For example, suppose we want to know the height of a male that is taller than 80% of college men. So we want to know the height of a male who's taller than 80% of college men. So this time you're given the probability or the percentage and you're trying to find the bound. Here we're talking about the 80th percentile. We are looking for the value of little x, the height, that is taller than 80%, 0.8, of college males. Little x is called a percentile ranking. There's a function in R for this as well. It's called Q-norm. So Q-norm. The inputs to Q-norm are the probability in decimal form, so 0.8, the mean, and the standard deviation of the distribution. So we see that a 74.61 inch tall male is taller than 80% of college men. Now, the drawback to this function, Q-norm, is that there is not an option to see a graph. If you would like to see a graph after you run the Q-norm function, you could go back and plug the percentile ranking, the output of Q-norm, into the P-norm GC function to verify that you got the correct probability and to get a visual of what you're looking at. So let's try this. So it should be that the probability that a random variable is less than or equal to 74.61, a left-tail probability, is 80% or 0.8. So let's flip over to our studio and just give this a try with P-norm GC. So we'll do P-norm GC, and our value was 74.61, the mean 72, and the standard deviation was 3.1. And let's output a graph, and I'm missing one thing, the region. So this region is below. I'm talking about a left tail probability. So let's give it a try. Okay, so you see that the probability that's output is 80%, and here you get a graph so you can just verify that the 74.61 was in fact correct. The last part of our Chapter 7 discussion will be about approximating binomial random variables. We're going to learn a lot more about this later, but while binomial and normal random variables are fresh in your head, let's go ahead and throw this at you. A normal distribution is a pretty good approximation to a binomial distribution if two things are true. One, if there are at least 10 expected successes. In other words, if n times p is greater than or equal to 10. Two, there are at least 10 expected failures. In other words, n times 1 minus p is greater than or equal to 10. If those two things are true, then the normal curve, the smooth normal curve that we've just been talking about, is a pretty good approximation to the binomial distribution. Remember, the binomial distribution was a histogram. You're going to see why this is useful in upcoming chapters, but let's take a look at this app, Binom Norm, in R to just sort of get a visual of how this is working. So I'm just going to copy and paste this code into our studio. Your manipulate wheel pops up, and what you see here is you see the histogram of a binomial random variable where n is set at 5 and p is set at 20% or 0.2. Now I know this histogram looks just a little bit different than the histograms you're used to seeing. These spikes are just in place of the bars that you typically see when we plot histograms. So right now p is at 0.2, n is at 5. So the expected number of successes for this binomial random variable would be 1, 5 times 0.2, and the expected number of failures would then be 4. Notice that both of those numbers are less than 10. So what we just talked about with the approximation is that if both of those numbers are greater than or equal to 10, then we have a pretty good approximation to the normal curve. So let's just check the checkbox and show the normal curve. And you can see that normal curve here is plotted in red, and you can sort of see how the histogram doesn't quite follow the normal curve. It's okay, it's not great. So let's just increase the number of trials. We'll leave p alone, and we'll just increase the number of trials so that our expected number of successes and expected number of failures are at least 10. So let's just make it big. There we go. Now you can see that the histogram and the normal curve very much resemble each other. So when those two things are true, at least 10 successes, at least 10 failures, then a normal curve is a very good approximation of a binomial distribution. Think about what this says. We can use a continuous random variable in place of a binomial random variable if our number of trials is big enough. The last app that is listed on here for you to play around with is just another example of this binomial approximation. So if the expected number of successes or failures is too small, then our approximation is not very good. So we'll just run this really quick, and then we'll close out chapter 7. So copy and paste. Let me make this window just slightly bigger. So now we have n set at 50. N's not an option to be changed, but you can change p. And this app is pretty nice because you can actually see the expected successes and the expected failures. So here we have at least 10 expected failures, but we don't have at least 10 expected successes. So let's just check out what the normal curve looks like. You can see that it's not a great approximation to the binomial distribution here. The expected number of successes is too small, even though the expected number of failures was big enough. And that wraps up chapter 7. Thank you for watching.